Thank you for attending this webinar on Lambda architecture design using Azure Databricks for advanced analytics. My name is Lucas Fyoke, and I'm a senior consultant with Kaizen Technologies. I've been with Kaizen for 5 years on the data and analytics team, focusing on data warehousing, reporting, and advanced analytics solutions. Kaizen is a Microsoft Cloud Solutions provider and Microsoft Gold certified partner. We provide solutions to complex business problems and assist companies in their digital transformations. Kaizen also offers strategic road mapping, application development, and 24/7 help desk support. For our agenda today, we will review Apache Spark and the company Databricks. Next, we'll cover Lambda architecture and real-world use case examples. Then we will see an implementation of Databricks in Azure with multiple services. Then we'll wrap up the webinar with a demo of Databricks Delta, which improves and simplifies Lambda architecture. Now let's dive into Apache Spark's history and the company Databricks. Apache Spark is an open source data processing engine initially developed by Matei Zahara at UC Berkeley AMP Lab in 2009-2010. Other students and professors worked on Spark and custom solutions for multiple customers. It was donated to the Apache Software Foundation in 2013 and quickly became a top-level Apache project. Apache Spark is one of the most active open-source big data projects with many contributors and companies. Here on the slide, it shows improvements over MapReduce and the Hadoop engine. This is done by utilizing what is called resilient distributed data sets. These are read-only sets of data that is distributed over a cluster of machines within shared memory. This speed up in processing allows for a more interactive data exploration to quickly obtain results. Another important aspect is Apache Spark does not require Hadoop and can access multiple sources of storage. Apache Spark consists of 5 main components. First is the Spark Core API and is the foundation of the engine and handles running jobs. This is where the resilient distributed data set is exposed to multiple language interfaces. Spark is written in the programming language called Scala, and it's the native language to work with Spark. Listed in the middle of this slide are the different interpreters that are used to interact and submit Spark jobs. The second component is Spark SQL and data frames. These provide an abstraction to the structured and semi-structured data in your storage locations. This is an ANSI SQL compliant language, and the engine takes those SQL statements and translates them into a Spark job and is submitted to the cluster. The third component is Spark Streaming, which has a fast scheduling capability to ingest data. This is how Lambda architecture is incorporated into our data lake. The next component is Spark's distributed machine learning framework called MLlib. The fifth component is called GraphX and is used for graph data processing. Next, to see an overview of Databricks' unified analytics platform, we start with Apache Spark being at the center of this product. It has the capability to connect to a variety of data sources, including IoT and streaming devices, cloud storage, data warehouses, as well as Hadoop storage. Databricks is currently available on Azure, Amazon Web Services, and other serverless environments. The Google Cloud Platform, GCP, is on Databricks' roadmap and is scheduled to be available later in 2019. Databricks provides an increase in the I/O performance over the native vanilla Spark runtime. Databricks Delta gives a higher performance and reliability for data lakes, which we'll cover later in the demos. With collaborative notebooks, the three main roles can work together and increase productivity. Since it runs in the cloud, enterprise security is available and managed in Azure or AWS. Databricks is certified for SOC 2, ISO, HIPAA, GDPR, and is planning for the FedRAMP later this year. Extensible APIs are available for working with external visualizations and other data sources such as Power BI, Tableau, and Looker. Now that we've seen Databricks and Apache Spark, let's take a moment to review the user interface and the different additions available to us. Here I have navigated to the Databricks website, and there is a link in the upper right-hand corner called Try Databricks. On the left-hand side is a free 14-day full-featured trial. This is a good way to try out integrating Databricks into your company's existing cloud environment. The Community Edition on the right is what we'll focus on today. It has a single driver node and no worker nodes. It's limited to 6 gigs, has basic notebooks without any collaboration, and the ability for 3 users to share the driver node. Clicking on Getting Started will require you to enter your information and sign up. The Community Edition runs on AWS and leverages EC2 Spot instances. It's a great way to get started using Apache Spark and learning Databricks. So now let's switch over to my Community Edition to get an overview of the user interface. This is the main portal for the Community Edition of Databricks. On the left-hand side, we have Home, Workspace, Data, Recent, Clusters, Jobs, and Search. Home will return you back to this page. Workspace shows the folders and notebooks available on the driver. Recents will show all of the most recent notebooks you have opened. Data will show us the data sets that we have available on the cluster. It's showing here that there's no cluster available, so we will need to create a new cluster. So under clusters, we have interactive and job clusters. For this, we'll create a new one and we'll give it a name. Cloud Pass Virtual Group. The runtime version is based on the version of Scala and Spark. There are multiple versions that are available, and supported versions are kept available to us. The ML versions contain pre-installed machine learning libraries, including TensorFlow, PyTorch, Keras, and XGBoost. Also, for distributed deep learning, Horovod is made available. For this example, we'll remain with the 5.3 runtime version. The default Python version has been set to 3 since version 2 will be sunsetting in 2020. Availability zones have the machine type available at certain data centers. Since this is hosted in AWS and uses spot instances, the clusters can be limited and service can become available at certain times. So now that we've given this a name, let's click Create Cluster. And while that's getting spun up, we can switch over to our workspace and create a new notebook. Under Workspace, I'll create a new folder called Cloud PVG. In that folder, I'll create a new notebook called Intro. The different languages available can be selected here for the base language of the notebook. For this example, we'll keep it with Python. Since our cluster is now available, it will automatically detect and assign it to the notebook. So now we can go ahead and hit Create. With the notebook created, here are the controls on the toolbar for working with the notebook. We can attach, detach, restart the cluster, or detach and reattach the notebook to the cluster. Under File, we can clone, rename, move, delete, export, or publish this notebook. We can also view the code or the results only. Permissions is unavailable in the Community Edition. Run All will execute all the cells in the notebook. Clear will clear the results, the state, or a combination of those. There's also a couple quick links to publish, make comments, and view the revision history of the notebook. This keyboard icon will show the multiple keyboard shortcuts available in the notebook. A notebook is really a collection of runnable cells or commands, and there are 2 modes for a notebook: command and edit. These modes are for each cell, and edit is when you are writing inside of a cell, and command is when you're working with a cell after it's been executed. Now we will work on the first cell and add 2 numbers together and then run the cell. We'll say 5 plus 5 and click this button to run the cell, and we get 10. The keyboard shortcut to run a cell is Control Enter. Next, we can add a new cell by clicking the plus icon in the middle of the cell. A really nice feature of notebooks is the ability to include text alongside your code. We could say, this code loads the data into the database, and then add another cell to do just that. However, this is just plain text. To improve the quality of these notes, we can use what is called magic commands to change the cell and how it gets executed. For example, we can use what's called the MD command to include various types of documentation, including text, images, mathematical formulas, and equations. This magic command will change the contents of the cell to be marked down and rendered into HTML. Next, we can copy in a link and have it be displayed as an image. Also, if we're working with mathematical formulas, we can copy in code specific to writing equations. In this example, it displays the Pythagorean theorem. Next, there are other tools available to access the underlying file system of the driver node. The Databricks file system, or DBFS, is a distributed file system that will persist to S3 and save your data after the cluster is terminated. Here, we will run a command to see the DBFS folder. And each one of these is a folder within the DBFS file system. Next, let's download a file and view its contents. We'll download the common iris dataset and display the first 10 rows. The SH allows for executing shellcode inside of the notebook. So we'll use the standard wget download from the this machine learning database library and save it as the iris CSV file. And here we see it's downloaded successfully and the head or the first 10 records of that file. Now, if we go back and rerun this section or this cell, we will see that that new file is now available. Now that we have a good overview of Databricks and Spark, let's switch gears and focus next on Lambda architecture. Lambda architecture was coined by Nathan Mars while working at Twitter on the Apache Storm project. His book listed here, Big Data Principles and Practices, is a great introduction and has in-depth examples of how to use it. Lambda architecture is designed to be a generic, scalable, and fault-tolerant system. In the book, it builds an example big data application called superwebanalytics.com that builds out a service to track page views per day. The idea of microbatching is also presented and discussed. I highly recommend this book if you're looking for a starting point for implementing a streaming architecture. Now let's see an overview of Lambda architecture's design principles. We start with traditional batch processing, where applications and source systems generate new data and often save it in online transaction processing systems. Then an ETL process is performed multiple times throughout the day, or maybe a nightly routine, and saved into a master dataset or a data warehouse. Then the users consume that data through a serving layer that offers views and tuned queries for reporting and further analysis. There are also ad hoc queries that are sent to find new information and allow business analysts access to that data in a clean format. However, this process can be stale. The data can be maybe a day old or a couple hours old, and many companies would prefer to have a near real-time look at their business operations. With Lambda architecture, it introduces a new speed layer, and a copy of the data is sent to the speed layer and is considered to be transient. This means that after a time frame, the data is removed from this speed layer and then saved to the data warehouse. Typically, these real-time views are considered to range from a few milliseconds to maybe even a few minutes. The data is being delivered at a rate that the batch process would just be unable to perform. Both the real-time and batch views can then be joined together and presented for further analysis. This architecture requires setting up and managing these two processes. But next, let's see how Databricks can stream data. As we saw on a previous slide, Apache Spark has a streaming component. Databricks has built upon this component and introduced structured streaming to reduce latency and allow for incremental processing of data. This is a high-level API and allows for running queries on tables that contain streams of data as it's being streamed in. The data stream is treated as a table and it's constantly being appended to. Data is received in an ordered fashion and is processed as it arrives to always remain consistent. This is also a fault-tolerant process, meaning that if an error occurs, the cluster will recover from that error without any manual intervention. When stream data is saved, any queries that are reading from this table will get automatically refreshed with the latest records. So some examples listed here are that leverage Lambda architecture. Credit card companies and banks handle millions of transactions a day and detect faults and fraudulent activity, which is very important to have a reliable service for your customers. We can think of automobile manufacturing assembly lines that have robotic arms to weld and assemble doors and components. Networks are under constant monitoring for malware and other types of unwanted traffic. Website traffic is also a good example of viewing hits on a site or activity for specific areas of your website. Algorithmic trading is used to minimize the risk of errors in execution of large market orders between traders. IoT and connected devices today are constantly sending information and feedback to the manufacturers. Now that we have some idea of Spark and Databricks and now Lambda architecture, how does all this fit together? Next, we'll wrap up with the slides and review an example solution architecture. This example architecture takes data from custom business applications and combines them with logs, media, and files. The data is copied from each source into an Azure Blob Storage account using Azure Data Factory. Azure Databricks is then used to clean up and pre-process the data. It may also run machine learning processes to find insights into the combined data sets. Next, it is sent to Azure SQL Data Warehouse for increased performance and a modeled schema. This can then be directly consumed using Power BI to the data warehouse, or an Azure Analysis Services can be added for further increase to performance with in-memory technology. Finally, business and SQL analysts would have dashboards that could monitor the combined business processes in one place. In addition, the ecosystem is continuously growing. There are many vendors that are integrating and leveraging Databricks into their own product. From visualization tools and applications to databases, messaging systems, and development tools, Databricks is becoming central to many modern solutions. Now that we have an understanding of Spark, Databricks, and Lambda architecture, let's review Databricks Delta. Databricks Delta is the next generation engine released from Databricks. It uses version Parquet files, transactional or Delta logs, and indexes and statistics to improve the quality of data lakes. This makes data more reliable and always ready for analytics. This new engine allows for batch, streaming, updates, and deletes to be performed on a single distributed table. The key features are listed below, and we'll review each one. ACID transactions are serializable and use optimistic concurrency to allow multiple users to write to the Delta log. Schema enforcement ensures data integrity of the ingested data and avoids data corruption with incorrect or invalid schemas. Delta tables support upserts as well as deletes to deal with changes. Previous standard Spark tables are write once and cannot be modified. Data versioning is contained within the transaction Delta log to support the minimum reader and writer versions separately. This guarantees backwards compatibility of tables and the occasional break in forward compatibility. Compaction is required to run on tables regularly using the optimize command. This prevents having multiple files that need to be opened and closed, and instead combines them all together into a single file. Caching in Delta is similar to Spark caching, and they both can be used at the same time. Delta caching detects when a cache file is created or deleted and then updates them. Cache can be called manually if it is required for consistent query performance. Data skipping uses file level statistics to perform additional skipping of files during queries. This feature can be used with partitioning, which will increase the query performance even more. This is enabled by running a create data skipping index on a Delta table. Along with data skipping, you can use Z-ordering to allow data skipping to co-locate related information within the same set of files. Now let's take a look at the difference between Lambda and Delta. Delta is a vast improvement upon the traditional Lambda architecture. Instead of having to maintain two sets of layers similar to Lambda, Delta is a single table approach. We start by collecting multiple data sources and save them to their corresponding raw tables. This is then parsed into query tables and then can be joined together with other query tables or with dimensional tables. Summary tables are business level aggregates that contain things like number of web page clicks or number of events that occurred. And then you have the final dashboard report, which is used for actionable insights and business metrics. These are also called different, these have different terminologies within Databricks. The raw table is called bronze, the query tables are called silver, summary tables are gold, and the final dashboard is considered platinum. Now let's switch to see a demo on how Databricks Delta can be implemented. In this demo, we will log into our Azure account and click Create a new resource. Next, we'll search for Databricks and click on Azure Databricks. Next, we'll click Create and we'll give it a name, Cloud. We'll give it a new resource group, Cloud, and we'll leave it in the Central US, and the pricing tier will be Standard. Now we can hit Create, and this will take just a few moments to spin up. Now that that has successfully deployed, we can click Go to Resource and launch the workspace. In the previous demo, for Community Edition, the UI is similar as it's shown here in Azure Databricks. To start, we will create a new cluster and give it a name. Let's be Cloud Pass Virtual Group. And notice there's a few more options available to us. For autopilot options, we have the ability to enable auto scaling and to terminate after so many minutes of inactivity. For now, we'll keep with all the defaults and go ahead and create this cluster. While we're waiting on that, I've gone ahead and prepared two files. The schedule file contains flight information between airports that are and their expected time of departure and arrival. I also have another file called track that will contain the list of locations that the flight is in during that schedule. To get these uploaded, I can simply drag and drop them to the Azure Databricks user interface, and they will automatically be uploaded. With our new cluster created and the files uploaded, let's start building out a real-time Delta dashboard of flight data. We'll go into Users, My Account, and we'll add a new notebook. We'll call it Flight Track. We'll leave it as Python and leave it with the cloud PVG that we created before. We can locate the uploaded files with the following command. Remember, the sh command is for shell commands to be executed. So here we're listing out the contents of the tables folder. Next, we can look at the top 10 records for each file and see what's in them. Here's the schedule, and here's track. Next, we want to read the schedule file and create a Delta table. In order to do that, we first get a SQL context, read in that CSV, infer the schema, and write that Delta table to a Delta folder named Scheduled. Next, we'll do the same for the track table. Now that we've created both Delta tables, let's have Spark recognize them and read them in as Delta tables. Here's the track stream that we're going to be streaming all of that information one record at a time. With the schedule file, it will be a batch, so we only need to read and not read stream of the schedule folder. Next, we can combine these two queries together and create a summary table. Now that the stream has been initialized and the combined query is being saved to a summary table, we can create new metrics that can be streamed to our live dashboard. Our first metric will show the number of flights flown. Our second will give us the min, max, and average ground speed. Our third will be the min, max, average of altitude. The fourth will be the time of flight landed. And the fifth is the most recent date that data has been received. Now we can run each of these metric queries. And when that stream has been initialized, we are then given a new button that allows us to add to a new dashboard. This dashboard we'll call Flight Track. And notice the number of flight has been displayed for us and is currently processing new data. We'll go ahead and kick off the others. And add each of them to the same dashboard. To do that, we click on the previous flight track that we created, and it will automatically show up on our dashboard. Once we have the dashboard laid out the way we would like, we can click on Present Dashboard, and that'll give us a nice user interface to be able to watch as things happen in near real time. I hope you found this webinar interesting, and if you would like to learn more, I will upload those slides where I have added multiple links to the presentations on how to get started, as well as how to access the community edition. Also, different blogs that have been helpful. A whole lot of videos. as well as projects and papers on the originating start of Spark. So with that, if there's any questions, please let me know. And thank you very much for attending. After some time had passed, we see some differences in the data and how it's being streamed in. Things are getting updated, as well as new flights are being brought in, and flights are landing.